Hey everyone, how are you all doing? So, the plan for this stream is that today we are going to test the VM translator. So, yesterday I think we were done with all most of the logic, but we are trying to check it if it works for this different programs. And I think we were testing this stack test, and we were getting I think mixed results, so we are going to try to test it again today. Okay, so to test the script we need, let's see, we need a CPU emulator. So let's fire up the CPU emulator. And let's also open up the VM emulator as well. So first we are going to test this techtest.vm. So let's open up this test file, this one, techtest.txt. All right, let's walk through the program step by step. The assembly file has been loaded. So this is the output assembly file that was generated using the VM translator that we built, and we are going to test if this code generated by the VM translator is correct or not. Okay, so let's go to stack arithmetic, stack test, stack test. Let's try to walk through the program step by step. So when we click single step, this will load 17 inside the E register. After that, after this first step is executed, we will have 17 inside the data register. After that, we are selecting the stack pointer and we will store this 17 value on the top of the stack. So as you can see, this is the stack segment and we have stored 17 on the top of the stack. Let's step through it again. Now we are going to increment the stack pointer. So now the stack pointer will have 257 as the value. As you can see, this is the value of the stack pointer now, 257. After that, we are again going to load 17 inside the data register. Again, we push this value on the top of the stack. So now we have two values, 17 to 17 values on the top of the stack. Again, we increment the stack pointer, which is this step. Now this equality instructions will be executed. So first we are selecting the stack pointer and decrementing it. So now 257 is the value of the stack pointer, and we are storing the value, this value, inside the data register, and we'll store this value inside a variable y, because this value is y and this will be the x value, and we'll compare between the both of the values if x is equal to y or not. So now we have stored this 17 value inside a variable y. So this is the variable y. Variable starts from this position, this memory location 16. So as y is the first variable inside our program, it is at 16th location. After that, we decrement the stack pointer again to select the x value, and we store it inside the data register. Again we get another variable x. This time, as you can see, it is at the 17th location because it is the second variable. We'll store it over here. So now this 16 is y variable and 17 is x. Now we will do x minus y, and it will give us value inside the data register. So the value is now 0 after we have done this x minus y step. If it is 0, that means both of the values x and y are same. So for that we are using this jump equality condition. Jump if equal to, we will jump to this label equivalent, and this label location is 109. So because this condition is true, we should jump to that location, which we do. As you can see, we are at the 109th position now, and here what we are going to do, we will store one inside that on the top of the stack, because the condition was true. If it was false, we would have stored 0 like this. So for that, we are again selecting the stack pointer and storing 1 on the top of the stack. So now we have 1 on the top of the stack. This is the top of the stack right now, 256. After that, we increment the stack pointer again. Okay. Okay, so this is the point where, okay, I see now why we were having this bug. So now the execution starts from this point onwards. Okay, great. So let me tell you what exactly is the problem. So we are first executing this set of instructions. After that, we are executing these instructions, and after that we are executing these instructions. Wait, it is correct, but you see, this is the problem. We are storing 17 value inside data register, but here somehow we are getting 892. Now this is the thing I was not being able to catch, why exactly this is happening. So maybe this step is being executed because here we have 892, but then I wonder where are all. So first we executed this up to this point. Okay, wait. Maybe the bug is occurring because we have this labels occurring multiple times in a single program. Okay, so we have EQ label over here as well. Also, it is over here as well. So that might be causing the problem. Okay, I see now. So that means we have to fix this problem. We can't keep using, so let's check the code. Where is the, these are all the right arithmetics. Do we have labels inside there? Yeah, we do have label. So what I'm trying to say is just like this label LT, we have this label LT. So now we can have multiple less than instructions in a single program. That means we will have this label, this particular label LT inside the single program multiple times. So that's why the emulator is getting confused as to where it should jump, or the assembler is getting confused. So the assembler might be assigning the last scene value or the first scene value of this LT. So we have to fix this bug. But what can we do exactly to fix this bug? One thing is for sure, we can't hard code this value LT because we can have multiple labels, multiple times this instructions occurring. Okay, to solve this problem, what can we do? We do need to use this label, but wait, the same goes for this variables. Just like labels, we will have this x and y variables multiple times. That means we have to do something with this labels and variables. What else do we need to take care of? Let's see. Here we have this address variable. What if after the variable name we add a digit, a particular digit like address 1, address 2, and we keep incrementing it after the use? That might solve the problem, but let's see how we can keep track of this variable. Let's take this LTC less than instruction as an example, and let's take this y variable inside that example. So when we come across this less than instruction for the first time, we should have y variable. Now this y, we can't just use y as the name of the variable, we should use something like y0. So that means this is the first time we have come across this, but we have this variable y inside multiple instructions. That means we have to take a variable name like something like ylt, which describes that this y variable is related to this lt instruction. And after that, we can't just use ylt because even the ylt instruction can occur multiple times, so we have to use something like ylt1, ylt2, ylt3, and so on. So probably we'll have to, but it will be much more complicated to track all the variables, because like we have, how many variables do we have right now? We have x, y, address, again we also have labels like lt, gt, pq. So that means okay, so I think this is something ideally the assembler should take care of it, I guess. It should be used something else like a memory segment or something. Wait, let me see. It doesn't matter even if we have this variables multiple times, because we are going to change the value of this variables anyway. So even if this y variable is called twice, inside twice inside for LT instructions. It doesn't matter, because suppose first time we get this y variable and we assign a particular value and we do some calculations. Suppose after that we again call this LT command second time. That time also we are popping something off the stack and assigning something on this y variable anyway, so it doesn't matter in case of this x and y variables. Is it the same with this address variable? Let me check. Yeah, we are going to change the value of this address variable as well again, so it doesn't matter however many times we call this variable. Okay, so that means we don't have to take care of this variables, but still we still need to take care of this labels anyway, because suppose we call this LT command, LTC command for the first time. Right, but the way assembler is constructed, what will happen is it will, whenever it will do the first pass, so our first pass is something inside the assembler, and if you don't know it already, we built the assembler in the previous stream. So inside the assembler, whenever it will come across a label for the first time, like this one LT, it will store the value of the instruction, the line number of the next instruction, so SP. So let me show you the program. So what I'm trying to say is, whenever it will come across, where's the label, where did it go? So whenever it will come across this EQ for the first time, it will store the value 40, not exactly 40, because we are going to get rid of this space and this comment line as well. So let's just for the sake of example, suppose we are storing 40 for the label EQ. So what will happen after that is, when we do the second pass, second pass is basically when we try to execute each and every instruction. So during second pass, when we come across this this instruction at EQ, it will look up inside the symbolic table where we store EQ is equal to 40 in the first pass, and it will store that value 40 inside the address register. And after that, when this if this condition is true, we will jump to this instruction 40, right? So that will be for the first time, that will be for first time when we come across this label. But now this EQ label might come twice inside the same program. So we also have EQ, the same label, at line number 84. So what will happen inside the first pass is it will store whenever it, yeah, I am from India, Nico. Not Bangalore, I'm from Gujarat. Why would you think I'm from Bangalore? Is it because all the IT professionals live in Bangalore? Alright, so when we do the first pass, we'll be storing 40 inside the symbolic table for this EQ label. But when our assembler comes across this EQ label for the second time inside the same program, it will ignore this uh, second instruction because we already have the value for EQ inside the symbolic table. So that means when we come across this instruction inside the emulator, it will jump to that 40 instruction again. So that's the problem. All right, so how do we solve it? Are you from India as well, Nico? So in the case of labels, we will have to store a state variable which will keep track of how many times we are coming across this particular label. So what I might have to do is, but again it will get much more complicated because we don't only have one label, we have multiple labels. So in this case we have LT, GT, EQ, and what else do we have? Inside this program we have this no label inside the push. Okay, so there are no labels in case of push and pop statements. So probably we'll have to take care of labels inside this logical statements only. Can we even get rid of this labels? I don't think so. So let's just use the state variable. We'll keep track of how many times we are Right, so I was saying we have to keep track of how many times we are having this label. But it's just a hacky-sacky solution. I want something which is robust. So I might keep track of how many times we are calling this LT instruction. Yeah, let's just keep track of the instruction counter. So let's get a variable for LT counter, LT count, and it will be 0 initially. The same for GT, EQ. Oh, so we only have to take care of 3 variables. Okay, it won't be that much complicated then. This will be for GT and EQ, I guess. And this counters will be 0 initially. And we will increment the counters here. No, we'll increment after we have assigned it to the variable. So we'll increment over here. We'll do self dot lt count plus equal to 1. This will increment the counter, but we don't just want to increment it, we want to assign it to this label as well. So we'll have to change it. So we'll have to replace. So we not only we have to replace this, we'll have to replace the variable with okay. So every time we are calling this method, okay, I can directly pass that variable over here like this. So I can do something like this. Instead of doing that, let me get a formatted string so that I can embed a variable inside the string. And over here I will do something like this: lt count. Okay, want the same thing over here as well. So what will happen is when we call this method write arithmetic, and this data we will assign. Okay, wait, this should be self.lt count. self dot. So this will take care of assigning the count. So when we call this LTC for the first time, we'll have at LT0 as the instruction, and when we call it for the second time, we will have at LT1 and so on. So let's try to test it just for this LT instruction. VM translator. We'll call the VM translator again, and we will pass stack arithmetic, stack test VM. This will give us a new generated code for the assembly. Now let's check the code. Stack test .asm. Let's check LT. Where's the label? Okay, so as you can see, we have LT0, LT0. Let's check a second LT instruction. This is the second one. In this case, it should be LT1. Yeah, it does contain LT1. So that means this is going to take care of our issue. Okay, so let's copy the same thing for GT and EQ as well. This should be GT count. Now we want this over here as well, EQ, and this should be EQ count. Okay, so let's now try to test the program again and see if it works without any bugs this time or not. We'll have to load the test file again. What the heck happened? Okay, wait, I think I messed up somewhere. Let's check the assembly file of wait. Yeah, I see. I have not created the formatted string. It should run just fine now. Let's load the test script again. All right, So let me open up. So let's try to walk through the program again. I think I'm going to skip this first part up to at least up to this m is equal to m plus 1. So let's try to run it. Now we come across this EQ0. Wait, this is fine and all, but still, why the hell do we have this 892? It should be 17. Why is this happening? Here we didn't have any problem. In this case, we are getting are we still jumping to different part? Maybe my assembler is not assembler. My translator is not working correctly, or maybe that isn't working correctly. Clearly, this instruction 892 is after this 3 instructions. Where are these 3 instructions anyway? Oh wait, I see. So what was it? Where's the EQ label? Over here, 20 on line 28. Just this one, EQ0. Now this EQ0, this shouldn't be 109. It should be where is the label? It is just at the stack pointer, so at 0. After we assign 0 to M33. So at this 28th step, we should have at 33 instead of 109. Why do we have 109? What exactly do we have at 109 location? We have this label, so probably it is, I think it is this one. Or It might be this one. Oh hell, silly me. I know why it is happening. I'm not even incrementing the variable over here, so I wrote this logic just for LT. I need to increment for GT as well. And same for EQ. Let's load it again. Okay, let's check the instruction. Where is it? It's over here. Okay, so we are getting the correct line number this time. It is 33. Okay, finally. Let's try to walk through it again. Before that, let's open up this file. From here onwards, this EQ, the instruction for EQ will be executed. We should have one inside the address register, I guess, on the top of the stack. Yeah, we do get one. After that, we will increment the stack pointer. Awesome. Now we'll come at this instruction and we'll load 17 inside the data register. After that, we select the stack pointer and store 17 on the top of the stack. After that, we'll store 16 on the top of the stack. 17 and 16. Now we select the stack pointer we should have, so see this four instructions are redundant because first we are incrementing the stack pointer and after that we are decrementing it. So it is because this push instruction, it can appear without having this equal to instructions after push instructions. So that's why we have two times the same operation. But we should have inside this VM translator, we should have a logic where we again go through this program and search for this kind of redundancy so that we can again optimize the program. Okay, that aside, so where was I think we were at this instruction. We'll store the value inside the data register 16 from the top of the stack. After that we will store 17 at X position, and we will do X minus Y. So we'll have 1 inside the data register. So now we are at this. Okay, at 17 we load 71 inside A register and check the equality. Again, in this case it is not equal. That means we won't jump to at 17, at 71. We will continue with this next instruction. Okay, that is happening. And in this case we'll store 1 as the value on the top of the stack. So now we have 1 on the top of the stack. 257. Wait, why do we have 1? Shouldn't it be 0? What happened? So when we executed this at 0, it will select the stack pointer and it will store 0 on the top of the stack. Okay, I see. We have a bug. So after we execute this 3 instruction, this instructions are going to be executed anyway. That means we have to go around these instructions. That's a logical bug in our program. What should happen ideally is after assigning 0 on the top of the stack, we should jump at this point. Can we get rid of the labels completely? I should probably, if we are going to keep this logic, then I should probably get a label after this instruction. So for this SP instruction, and I should jump to this label unconditionally after executing this instruction m is equal to 0, so that this instructions won't be executed. And this is not just about this EQ instruction, we have the same logic inside many different instructions, so we'll have to change it for all the instructions. Oh damn. and that means we have to keep track of those labels as well. Is there another way so that we don't have to use another label? Wait, we are using this labels inside three logical instructions only. So that means we have to change the logic of those three instructions only. Let me open up the file. Where are the... Okay, so over here. So what is happening actually is when we check for this condition if less than equal to 0, we execute this, we jump to this step, and after that we execute this one. But inside our program assembly code, this instruction comes just before this instruction, so there's no logical flaw. But when this condition is false, we execute this instruction. Now this instruction is just before this instruction inside the machine language. That means after it is done executing this instruction, we change the stack pointer again to 1 anyway, so that totally makes these conditions totally useless. So we have to write something so that only one of this condition, either if or else, gets executed, not both of them. So to do that, I should use thing. I can use another, so I can write a label like this L and after we are done executing this 3 instruction, it will store 0. We should jump to that label unconditionally at lt and 0 jmp. So if these 2 instructions are done, we will jump to this lt unconditionally. So that might solve our problem, and we'll have to do the same thing for this gt as well. The same thing for EQ as well. Okay, so this might take care of it, but this is just the logic. I have to change this inside our program. Now I have to change it over here. So let's see where I have to change. Over here. It should be something like this, at the rate. This is for lt, so lt and comma. But we'll have to keep the counter in this condition as well. So let's get the counter first. This counter will be called self lte or end, lte and count. This will take care of it. And we should have a label at this position. Yes, this will work. Let's copy the same thing for this GT. gt, and we'll call the variable gte count. The label should be here. This is for gt. Now for eq. Oh wait, you still need to write the jump instructions as well. Okay, I will write it afterwards. Let me first write the labels. This should be eq and the variable eq count. I'm glad we don't have any more labels. Okay, now let's take care of the jump instruction. The jump instructions will come after this instruction. It should be 0 jmp. Okay, that's it. And the jump instruction will look same for all the commands. So let's copy it. Okay, this might take care of our issue. Wait, we still have to get the variables. We call the variable lt e count. gt e count and eq count. We have eq and 0, eq and 0. Alright, so now after it is done executing this instruction, it will load eq and 0 and jump unconditionally to this label. So this might take care of our issue. So let's load the script again. And let's see if it works or not. So it works for this instruction, so I'm going to just skip it over. Wait. That's a problem. We have 118, which is incorrect. Oh yeah, I know. We are not incrementing these counters as well. So we have to increment these counters. LT the counter. I'm doing the same mistakes over and over again. That means I have to load the program again. Well, I can just reset it. So let's try to run it now. Now we have 38. Good. Now we are going to execute the second set of instructions. Push constant 17. So now let's see. It should jump to this. We are over here right now. D is equal to D minus M. So the result is 1. We'll load at 75 to jump if equal to, which is not, this condition is false. That means we'll execute the next set of instruction, which will store 0 on the top of the stack. And after that we'll jump to this instruction unconditionally. Awesome, it is working. So now this value is not being overwritten, which is exactly what we want. Now we are going to run this set of instructions. First load 16 on the top of the stack. And after that we load 17. Okay, correct. Again we have 0 on the top of the stack, which is awesome. After that we are going to execute this set of instructions for 892, 891, and it will check for less than. So let's load 892 on the top of the stack. After that we load 891 on the top of the stack. We'll check for if 892 is less than 891, which is not the case. Now we will do 892 minus 891. Then we should have the result inside the D register. It should be 1. It is 1. After that we'll check for if it is less than or equal to. Jump to 155 if it is less than or equal to, which is not the case. That means we'll execute this next set of instructions. We'll load 0 on the top of the stack. After that we will jump to 158 unconditionally, where we will increment the stack pointer. Awesome. Now we are going to test for these conditions. First we will load 891. After that we'll load 892 on the top of the stack. I'm just going to rush through it because okay, so in this case it did jump to 195 because the condition is satisfied. 891 is less than 892. So in this case we'll store 1 on the top of the stack. So we do store 1. What do we have now? We are going to check for if 891 is less than 891. We should have 0 inside data register after we execute this instruction. So it is 0. Now this condition will not be satisfied, therefore we will continue with the next instruction, which will store 0 on the top of the stack. Okay, and after that we will unconditionally jump to line number 238, where we will increment the stack pointer. Awesome. Okay, now we have this set of instruction where we store first 32767. We'll show 32766 after that. So we have two values on the top of the stack now, 32766, 67 and 766. We'll check if 32767 is greater than 32766 or not, which is true. That means we'll jump to 275. Yeah, indeed we did jump. Therefore, we'll store 1 on the top of the stack. And sure we do. After that, we increment the stack pointer. Now we'll check for this set of conditions. Before I continue, I'm going to take a small break. Okay, we are at this instruction. We're going to load 32766 on the top of the stack. After that, we will show 32767. We are going to check for greater than condition. We'll check if 32766 is greater than 32767. We are going to check for greater than. Okay, so after that we are going to test the arithmetic commands. First we push 757 on the top of the stack. After that we will push 31. And after that we'll push 53. Okay. Now we'll add 31 and 53. Okay, we have the result of 31 and 53 on the top of the stack, which is 84. 31 plus 53, 34. What do we do after that? We push 112 on the top of the stack. Okay, what do we do after that? We'll subtract 84 minus 112. So 184 minus 112 is equal to minus 28, right? I guess so. Yeah, it might be correct. Okay, what do we do after that? Okay, we negate. So we negated the value from the top of the stack. We executed this set of instruction. After that we will AND 57 and 28. When we do AND of 57 57 and 28, we get 24 is the output. Okay, and after that we push 82 on the top of the stack. We do the OR operation. Okay, so after doing OR, we have 90 on the top of the stack. Now we'll do NOT, which is the last instruction. Minus 91. So if we jump to 266, this is this stack after we have done all the instructions. This is what we should be having at the end of the program. So starting from 256, we should have 1, 3 zeros, and 1, 1 0, 1, 2 0, and minus 91, which is correct. And again, this 1 is I think this 1 is being recognized as -1 anyway, so this is correct. It's just an implementation thing, because in our case we are storing 1 whenever the condition is true, but they are stored -1. Okay, this is our output, and this is their output. So that means we have to store -1. Okay, it's just a minor thing. We just have to change this 1 from -1, or else everything else is all right. So let me do that. Instead of storing 1, we'll store -1. We can change it over. Let's see where we can change it. Yeah. Okay, where else do we need to change? So let's load the program. Okay, wait, but first we have to get the new ASM file. Okay, so cool. Now we are writing -1 as the output, and in this time the comparison ended successfully. That means that's what we needed to change. And also let me change this file as well. Here -1. Awesome. So we have tested this one program successfully. We have tested simple add and stack test both of the programs, and they are running all right. So now we have to test for the memory access commands. We'll start with basic test.vm. So before we try testing it, we will have to get the assembly instructions. So let's run the assembler. Wait, not run it over here. Have to get the translator instruction for basic test. Where is basic test? Memory access basic test .vm. Now this should give us the assembly file. Memory test basic test.sm. Alright, so this is the generated assembly file. It is quite large, so it's going to take time. Let's load the test script. Memory access basic test.txt. Before we try to walk through this program step by step, let's let it run directly. Okay, we have a failure. This is our output, and this is the comparison file. These values look similar, but we have issue at this RAM values. So that means we have a logical flow. So we'll have to walk through the program step by step. Okay, let's start then. First we push 10 on the top of the stack. Let me clear all these values. So now we have initialized all the segment pointers. Stack pointer to 56, base pointer of local, argument, this, that. Okay, now the program execution begins. First we load 10 inside the data register and we push it on the top of the stack. Wait, what happened? Why didn't we jump to the stack? Let me try to load the program again. When we execute this command, it should jump to the stack. It is not doing that. Why the heck is it not doing that? It will be the pain in the ass to jump to those instructions. This means we will have to jump to that instructions manually. Well, 10 is pushed on the top of the stack. Now we increment the stack pointer, and again we select the stack pointer and push, no, not stack pointer, we store 0 inside the data register. After that we select the ADDR, just to get the variable ADDR, and we store 0 inside that value. Seriously, I have to go through it manually. Okay, I don't want to go through every time manually to that RAM, so I'm going to close this and open it up. It was not working correctly because of those error messages, I guess. I hope it works this time. So let's load the test script. This should initialize all the values. Okay, let's see if it works and jumps to that particular segment or not. Awesome, it is jumping to that segment. So yeah, it was probably because of those error messages. Okay, we push 10 on the top of the stack, then we increment the stack pointer. After that we are going to execute this pop local 0 instructions. We store 0 inside this address variable. After that we get the LCL pointer and store its value inside the data register. We have 300 inside the data register. After that we again select that address register, address variable, and we do m is equal to m plus D. Right, we have 300 inside this address variable. After that, we decrement the stack pointer and we store 300 on the top of the stack. No, value pointed by the 300. What do we do over here? First we pop. Okay, I see what happened. First we push 10 on the top of the stack. After that we popped this value from the top of the stack and stored that value at local 0, which is correct. We have 10 on the at the local 0 segment. After that we push constant 21. And push constant 22 on the top of the stack. What happens after that? We pop off the top of the stack and push it on at the segment argument 2. So let's see. Four hundred bus 2, 402. We have 402 inside the variable. Now we decrement the stack pointer. This is the value from the top of the stack 22. We pop it and store it inside that argument to segment. Awesome. So at 402, which is argument 2, we have 22. So this instruction is working correctly. After that we'll pop argument 1. So in this case we should have 21, I guess, inside 401. So let's see if this happens. Awesome, it executed and we have 21 on the, wait, no, we don't have it yet. Okay, now we have 21 at this segment. Now we come to this instruction, constant 36 will push 36 on the top of the stack. Okay, after that we'll pop this 6. First we'll store 6 inside the ADDR variable. Okay, it changed. After that we'll select this, store it in value inside data register D. We have 3000, which is the value of this, and after that we add this 3000 plus 6 and store it at ADDR. Yeah, we have 3006. Now we decrement the stack pointer and pop the value, store it inside the data. So we have 36. Now we have to store this value at this 6. This 6 was pointing to 3006. So now we have 36 at that register, which is correct, I guess. Okay, now we come to this instruction, potato. Push potato on the top of the stack. After that we push 45. Now we'll pop that. Okay, 3015 position, we have 45 stored. Cool. After that we'll do pop that too. Three 3012. We'll store 42 at that location. Okay, we stored 42. Now we are pushing 510 on the top of the stack. After that we will pop temp 6. So first we increment the stack pointer and we get a new argument to variable. Oh wait, is this skill correct? All right, I see. This is not correct. It should be so. Let's review. Right push pop. This is not correct. here we should have the value of arg2, not just arg2. Why are we not getting the value arg2? Even though this is a formatted string. Let's check the assembly code again. So just like we had 510 at this position, we should have the same value here as well for pop temp 6. So just like we had 510 from this position, we should have at 6 at this position as well. It should work. Why is it not working? Let's check other temps. In case of push, it is working. Pop, push, pop. Okay, in case of push, it is working, but not in case of pop. Oh, I see. What the heck? Silly me. So I will have to translate the program again. Let's run it directly. Yeah. Let's see if it is working. Okay, so that was the only issue in our program. So we are getting the same output as the compare file. So I don't think we need to walk through the program. We are getting the output same as the compare file. That means our logic is correct and our translated program is working for all the push and pop operations. So instead of checking step by step, let's test this different program now. Pointer test.vm. So let's get the assembly code for pointer test.vm. Pointer test vm. Okay, let's open pointer test.asm. Let's load the same program inside the CPU emulator. Pointer test.txt. Awesome. So this program worked as it should be. So both the output and comparison showing the same results, and we have got the message comparison ended successfully as well. All right, so now let's get the third program, which is stacktest.vm. This is the last one. This is the generated assembly file. Okay, static test, not stack test, static test. Awesome. This ran successfully as well. All right. So we have tested all of these 5 programs and we debugged our assembler, not assembler, our translator accordingly. That means our assembler, the implementation of assembler is correct. We don't need to do anything else inside our assembler. So that means we have successfully completed project 7, guys. Do we need to do anything else? We have tested the script. No, I don't think that it's anything else to do. So that means we won't be doing anything else today, and I'm going to end this stream here only. I'll get back to the stream, this project. We'll continue with project 8 in the next stream, but before that I will have to review the videos of the project 8 from the Coursera website. So once I'm done, I will get back to the implementation of project 8. Alright then guys, I will see you soon in the next stream where we will be implementing the project 8. Right, have a nice day or night, whatever it is for you. So bye bye.